Hello, good morning. I hope you're doing well today. All right, so we have to today finish our discussion about universal gravitation. In particular, we will talk about Kepler's laws. And then if we have some time, we will start talking about simple harmonic motion. Okay, so Kepler started making observations about the motion of the planets way before Newton's came up with gravitation law. So who is Kepler? He is a German mathematician, physicist, and astronomer. He make observation alone. So he's a founder of celestial mechanics, and he has predictions about how planets move, and all of that was based on his observation of the motion of the planets alone. Isaac Newton came up with the universal law of gravity, and that came up later than Kepler. Okay, so let me refresh my screen. You are not seeing the screen going up and down, so let me refresh it. So there are the Kepler's three laws about the motion of planets actually can be explained by the universal gravitation. So in some ways, the universal gravitation is more fundamental about the physics than Kepler's laws. Kepler's laws is more based on the phenomenon, based on more on the observation. But Newton said if he had been able to see further, that is because he's standing on the shoulders of the giants. So there was this famous quote by Isaac Newton that any observation and any discovery you make today was always based on all the work that people have already done before us. So let's take a look at Kepler's laws. Kepler's first law saying that the orbits of the planets are ellipses, they're not a perfect circle. And the sun is at one of the focal points of the ellipse. So the sun is here and the planet moving in this dashed line as shown above. That's his first observation, what he found out by his observation. Kepler's second law discovers that in equal amount of time that the planet sweep out equal areas. So this area is equal to that area in the same amount of time. That's Kepler's second law. Kepler's third law is giving us an equation that tells us how long it is to take the planet to go around. So the period of the orbit is proportional to the semi-major axis cubed. So this is considered semi-major axis A, right? Because this is an ellipse, that's why A and B are non-equal. So Kepler's third law saying the t squared, period squared, is proportional to this distance A cubed. And there's some constants here. So if we're talking about motion around the sun, you use the mass of the sun. And if this motion around some other planets, you will use the mass of that other planets. Okay, so this is a law of the period of the motion. So that's it. That's the three laws. The following exercise, the main goal is not really so much about, using this equation, because this is just an equation, right? You can plug in the numbers, you can always calculate the t. So there's not too much going on there. But I want to use the next few questions to show a way of calculation that is you're using the orders of magnitudes. Instead of plugging everything in and punching everything into your calculator, we wanted to represent something in this format, and only look on the orders of magnitude, and that really helps you to simplify that calculation. Especially here, we're dealing with astronomical objects, and all of these numbers are very big, right? You're dealing with very large distance, you're dealing with very large mass. So this kind of order of magnitude calculation or estimate, it will give you a good estimate is much more handy than if you had plugged in everything all at once. Okay, so let's take a look at the first question. So here we are given 4 different objects: Earth, the Moon, Pluto, Charon, different planets. And just like how Moon is orbiting around the Earth, Charon orbits around the Pluto. Okay, and the mass of each of these 4 are given, and the radius of the motion is of the planets is also given. All right, so given these information, the question asks which object exhibits the longest orbital period. So you can see this is really just an application of Kepler's third law, the law of the period equation. Is, well, if you want to compare T, let's see what is different for the different orbits. A is different and mass is different, right? So here we are comparing 2 different kind of motion. One is the Moon around the Earth, and there's a period there, and the other is the Charon around the Pluto, and there is a different period there. So we need to compare these 2 different times. And what's different is the A cubed over M is different, right? 4 pi squared and G, these are all just constants here. Okay, so then we have to decide, all right, so what kind of mass do we use? Well, we should use the mass of the central body, because earlier this was introduced, we were talking about going around the sun, we use the mass of the sun. But if you're going around the Earth, then you need to use the mass of the Earth. If you're going around the Pluto, then you need to use the mass of the Pluto. So that is the mass we need to look at. So we'll start this order of magnitude analysis looking at the first pair. The first pair is Earth and the Moon going around the Earth. Okay, all right, so we represent, you can see the Earth mass is given. So go back to where they give you Earth's mass. And all you need to write down is the order of the magnitude. So approximately it's to the power, is to 10 to the power of 24 kilograms. Because the difference between this time, on a good chance that they differ more than 10. So that's why we are not so concerned about these numbers in front, right? If one of them is 5 times 10 to the power of 2, another is 7 times 10 to the power of 3, you can see you obviously only need to compare the orders of magnitude and don't worry too much about these numbers, and then you can tell which one is bigger. So we're just gonna look at the order of the magnitudes here. Okay, so mass is on the order of magnitude, so you will say approximately 10 to the power of 24, and this is in SI unit kilograms. And the semi-major axis here is 378,000 kilometers. So we also need to change that to meters. So you can see, okay, 1, 2, 3, 4, 5. So that's 3.78 times 10 to the 5th 5 power kilometers, and then change to meters. That's another 3 meters. Okay, so that's why A is on the order of 10 to the power of 8 meters, but it's A cubed. Okay, so again, A cubed, you have to change it to A cubed. So that's A cubed is 10 to the power of 24 meter cubed. Okay, so now you can just plug in A cubed divided by the order of magnitude of the mass. You can see this is on the order of magnitude of 1. That's for the Earth and the Moon pair. That's the first pair we have. All right. Okay, so the second pair is between Charon and Pluto, and you can see that they tell us the distance between them. So that was your A, that is your A you're going to use for the second pair. Let's look at the second pair. The second pair, again, the mass, you need to use the mass of the Pluto. Okay, so how do we write this? We're going to rewrite this using 1.46 times 10 to the power of, you can see that's going to be 22 kilograms. Okay, so whatever in front of it has to be a number between 1 and 10. Okay, so the mass of the Pluto is on the order of magnitude 10 to the power of 22 kilograms. And do the same thing for A. So 1, 2, 3, 4. So that is 1.96 times 10 to the power of 4 kilometers. And that is 1.96 times to the order of 7 meters. Okay, so that is your A. And then cubed becomes 21, 10 to the power of 21. So you're looking at A cubed over mass, which is 0.1. So you can see that that shows this is smaller than the period of the moon. We simply only looked at the order of magnitude. Okay. So this helped us simplify calculation. If you had plugged everything in with all the zeros in it, that would be much more difficult. Okay. So that's the first question. Second question is very similar. Okay, second question is very similar. We are also still going to do the order of magnitude analysis. And in this case, we're looking at the escape velocity. So escape velocity, remember what is escape velocity? That is the minimum speed you need at the surface level of the planet in order for you to be free of the gravitational field of that planet. So which means when you are at your potential energy 0, your velocity is also 0. So you barely escaped. We had previously calculated this escape velocity is square root of 2 times constant g times the mass of the planet divided by the radius of the planet. Okay, so you can see here we're going to choose between these 4 different choices. Each of them have their own mass, right? Each of them have their own radius. So really, you're just comparing the m over r. Whichever has a bigger m, whichever has a bigger r. Okay. So this one, why don't you guys do this as a practice yourself? You can use a scratch paper that you have, and on the scratch paper, write down, okay, what is the order of magnitude for Earth? What is the order of magnitude for Moon, Pluto, and see which one you think is the smallest, okay? Smallest. All right, so so whenever you're ready, we can vote into our answer here. All right, so feel free to take a moment to calculate. We will wait until you have your answer calculated. And whenever you're ready, you can put in your answer. All right, so for example, if you were looking at the Earth, right, you would use the mass of the Earth's order of magnitude divided by the order of magnitude for the radius r. And you can see, okay, so we're using meters, right? This is how many orders of magnitude? 1, 2, 3 for kilometers, and another 3 to change it to meters. So that's 10 to the power of 6. So this will give you 10 to the power of 18. That is for the Earth. Okay, so you'll do the same thing for the Moon, Pluto, and the Charon to get whichever is the smallest. All right, we'll wait for 10 more seconds for us to wrap up. All right, I'm gonna go ahead and close this. Let's take a look. All right, it looks like we do have a majority of the vote on Charon. All right, very good. Let's just see. You probably already see that these are all on the order of 24, but these are all on the order of magnitude in thousands, but these are much smaller, right? So you right away, you can see that these two are smaller than the Earth. And they probably wanted to look at, okay, the smallest of this one to compare with Charon. But let's work out all of them. Okay, so this one is on the order of magnitude of how much? So if I write this using 7.3 times 10 to the power of, it has to be 22, right? So the mass is 10 to the power of 22 divided by the R, which is again 1, 2, 3, another 3, 10 to the power of 6. So that gives you 16, okay, smaller than Earth. And this one is 22 over 1, 2, 3, another 6. So this is also 16. This is also 16. Well, this one is 1, 2, 3. So that's 21. And this is only 2, right? This is 6 times 10 to the power of 2 kilometers. So that's 10 to the power of 5 meters. Also 21. Now this is the smallest for Charon. Okay, so yes, D is correct. Oops, did I the 14 here?
Professor, can I get another second?
I'm sorry?
Oh, sorry, can I have another second for that slide? Sorry.
Sure.
Thank you. I got it. Thank you.
Okay.
Thank you, Professor.
All right. Okay. And this is not 14. This is actually, oh, sorry. What did I miss? It's also 14. Okay, I believe this here I made a mistake. It's not the 14, right? What did you guys calculate to be? This 1, 2, 3, that's 21, and that is 5. So this is also on the order of magnitude of 16. So when you have more ambiguous that you couldn't tell right away, then you do have to plug in the corresponding numbers. So in this case, we would have to do 1.46. This is the mass over 1.185. That's the Pluto. This would be, okay, sorry. This would be 1.62 divided by 6.04. Okay, so you can still see this would be smaller than that one. So this is still correct answer, but this is not to the power of 14. Okay, so this one you do need to do a little bit more calculation of the actual numbers because the order of magnitude are the same. All right, so next we're going to look at a couple of examples of how to use Kepler's laws. Is in particular is the law of the period to look at the time of the orbit. Here we have our first question. We're looking at our sun. Well, all the planets rotating around the sun, but the sun itself rotates about the center of the galaxy at this distance. So here they introduce an idea, something called light years. Okay, so do you guys know what light year represent? When we say light years, what do we mean?
How much light in a vacuum travels in a year?
Yeah, the distance that light travels in a year. So this is actually a distance quantity. Okay, the dimension of light year is a length quantity, it's not a time quantity. So because in astronomical objects, if we use meters or anything else to represent the distance is too big. So that's why we're using units of light years to give us an idea about the distance. So here, okay, you have this much distance between the sun and the center of our galaxy. And we can convert that to meters. So how are we going to do that? Well, light travels in a year. So this is the speed of light. This is something we can look up in vacuum. And that's also something we should remember it because speed of light, we should all, right away remember what that is. So 300 million, so 3 times 10 to the power of 8 meters per second. So that is the speed of the light. With that speed, you travel for a year. So how many seconds is in a year? And you can plug in the number of seconds in the year. So for this one, you can say, okay, 1 year is 365 days, and 1 day is 24 hours. 1 hour is 60 minutes, and 1 minute is 60 seconds. So 1 year is this many seconds, and that's why we got the 3.16 times 10 to the power of 7 seconds. Okay, so this allows you to convert light year to a distance that's represented in meters. And the mass of the galaxy is also given. So we're asking what is the period of our orbital motion about the center of the galaxy in Earth years. Okay, so we are calculating the time, right? We are just going to use the equation. This is, you can see Kepler's law, there's not too much problem solving involved. It's really just plug and chug into our equation. All right, so I'm going to plug in the numbers here. And the distance, which is given, times 10 to the power of 8 times how many light years? Okay, this many light years. So is this many light years, and 1 light year is this thing. So I need to plug all of that in here. So I think the main benefit from doing this calculation, it's not too much problem solving, but we can use this to help us get familiar and comfortable with calculating large numbers and how do you simplify your calculation. And I will show you guys here. Okay, so that's our A, and G is this constant, and mass is given. Okay. And this is in meters. So if everything is in SI unit, you can choose not to put your unit here because you know that it's going to give you the correct unit of seconds for time. All right, so at this point, what would you do? You can see, well, that's too much going on. How do I enter this into my calculator? So we will group all the tens together. So what you do need to enter into the calculator are the ones without the tens. So it's 3 times 3 times 3.16 to the power of 3. And the rest will be the tens. So this is 10, 4, 8, 7, right? So this will be 10 to the power of 12 when you multiply these. 12 plus 7, that's 19 to the power of 3. So I'm going to move all the tens together. And here, the negative 11 plus 41 is 10 to the power of 30. Okay, so what you really need to calculate in your calculator is just this part. In this part, we'll leave it alone. Okay, so what does this become? When you do a power, the argument multiplies. So 19 multiplied by 3 and divided by, so 19 times 3 and divided by that, so you minus 30. So that will give you 10 to the power of 27. And all of this will give you 3.4, again, times 10 to the power of 4. So this is something extra you get from your calculator. Okay, so this is our total time, and you can rewrite this to be 34 times 10 to the power of 30 second squared. All right, so, but that's not the end of it. It's still asking us, okay, how do you represent that in years? So just give us an idea how long it takes to go all the way around the galaxy, because we are more comfortable with, we have a better judgment with years. We know how long 1 year is. Okay, so we change that to year. So the time is square root of this. Okay, so really you need to put into your calculator is just the 34, and this has become 10 to the power of 15. So you can see why I write 34 times 10 to the power of 30 instead of 3.4 times 10 to the power of 31, because I can take the square root of 30, 10 to the power of 30. I cannot do 31, right? So that's why I say 34 times 10 to the power of 30, and I leave this alone. I only do the calculation in my calculator for that one. So that becomes 5.8 times 10 to the power of 15 seconds. Okay, so how long is that? So we're going to divide all of that by that many seconds that's in the year. That's 365 days, 24 hours, and 3,600 seconds in an hour. So that gives us 1.8 times 10 to the power of 8 years. Wow, how much is that? That is 180 million years. So it's not going to go around the galaxy once in our lifetime, and not for many, many years. Okay, 180 million years. So that is, sorry, go ahead.
Sorry, could you go up and show the beginning of the slide again? I was just trying to see what it, yeah, right there.
Here?
No, a little bit down, please.
Here?
A little bit more. Yeah, there, thanks. Oh, what did you have below that on like the next page in your little, yeah, that's what I was referring to. Thank you.
Yeah. Okay, so
Oh, I got it. Thank you.
So you can see the physics here is there's not too much physics involved. Kepler's laws, this is only equation that we use to calculate things. The goal here is to get comfortable with writing things in scientific notation and how to do calculations. And you need to in practice putting your tens away on the side. So don't enter everything into your calculator, and that helped you simplify things, okay? And do an estimate on orders of magnitude, also that help you simplify things. All right, so that's one. The last example we will do for the Kepler's laws is this. again, very similar. It's application of the laws of the Kepler's period, the period of the planet motion. Here we're looking at our sun in the solar system, and tell us that it's actually not at rest in our galaxy. Well, we have already looked at the time it takes, right, to rotate around our galaxy. We orbit around the galaxy once every this many years, okay, at a distance of this many light years. So you can see this is a little bit different from our calculation above. Well, because we did previously, we simply did a estimate, right? How many seconds in the year? There's not always 365 days in the year. So what we did is a calculation, but in terms of the order of magnitude is on the order of 100 million years. So that's correct. Okay, so that tell us, okay, use this period and use this distance. All right. So you can think of the mass of the Milky Way were concentrated at the center of the galaxy. What would be the mass of the galaxy? Well, you can see this is similar to the previous question, except the knowns and the unknowns are switched. So here you're given the period and you need to find the mass of the galaxy. Everything else is the same. You can see to find the mass of the galaxy, you simply plug in into your equation with the distance and your period. Okay, period is already given to you. You need to convert this many light years, this many years into seconds. In terms of the distance, you need to convert this many light years into distance, which is in meters. So if you do that, you can get a number for the mass of our galaxy. Okay, so really, again, very similar to before. It's just what is given and what it needs to be calculated is different. Okay. All right, so that's all. That concludes our discussion for universal gravitation. Now you can see that the one major important equation that you need to remember from this chapter is the inverse square law describing universal gravitation is proportional to the mass multiplied together and divided by the distance squared. Okay, so there are a variety of different questions you can ask for this. For example, relate that to mass times acceleration. You can calculate the speed of the orbit, right? Or do a conservation of energy, saying, well, if you're at different distance away from your planet, what is your velocity? Now we can use our potential energy that is described in this formula in our calculation. So the one major important physics laws for this chapter is this equation. Now let's go to talk about simple harmonic motion. All right, just 1 second. Let me bring that up. So you probably are already familiar with simple harmonic motion because we actually did some of that in the labs. Some of you probably did lab 12, right? So simple harmonic motion is a very, very useful physics model. We can use the simple harmonic motion to describe a variety of different phenomena. For example, in here, we're just looking at, a spring. We have something attached to a spring and they're going up and down, a mass attached to spring and going up and down and up and down.
Professor, are you trying to share your screen right now?
I'm showing you in a second.
Oh, okay. Sorry. I just thought you were writing and yeah.
Yeah. And there are other things that follow a simple harmonic motion model. Later on, when we study, at the beginning of the semester, we talked about the pendulum. Okay, so we actually derived a equation for the period of the pendulum simply just using dimensional analysis. That's also simple harmonic motion. Later on, when you do electronics, when you do E&M, you will look at circuits. Some of these circuits, the current oscillate like a simple harmonic motion. So there are a variety of different applications for this model. So we are introducing it here. We'll start with a question by, okay, well, the easiest way to give a simple harmonic motion is to attach a mass to a spring and let it oscillate. All right. Okay, so we know that because the spring force, according to Hooke's law, is a restoring force, right? When you stretch it, it will pull you back. But when you compress it, it will push you out. So at which point the acceleration on the mass is the most positive? If we had set up our coordinates in such a way that to the right is the positive direction. So you can see that the oscillation is happening between this point when the spring is most compressed and this point when the spring is most stretched. And right in the middle here is the spring is relaxed, is neither stretched or compressed. Okay, so which one of these give you the most positive acceleration? What do you think? Don't have to vote, just you can talk about this or you can type in the chat.
I think it would be negative A, because if 0 is our equilibrium point,
Okay.
When it's at A, from the spring will be on the left trying to get it to 0. So that would be negative acceleration. But at negative A, the force is pushing to the right, trying to get it to 0. So that's when it's most positive.
Right, yes, very good. No force in the middle. And here, the force will be pushing to the left, give you an acceleration to the left. Here, the force will be try to push you out, and that's to the right, which is in our positive direction. So here, that will give you the most positive acceleration, okay, because the only force that's acting on the mass that give the acceleration is a spring force. So we will derive the equations of motion by using Newton's second law. And this is a very common technique throughout physics to derive the equations of motion. So when we say equations of motion, what do we mean? Equations of motion simply saying, well, I want to tell you exactly the trajectory of this object by giving you the position of the object as a function of time. I can tell you at what time, what position is going to be. So that is called the equations of motion. And we can solve that by using Newton's second law. Okay, so this is how we're going to do it. So we start with Newton's second law. This is something we are very familiar with. Simply F equals ma, right? And when you apply this on a simple harmonic motion where a mass is attached to a spring, here your force is a spring force. The spring force is negative kx. Okay, so here you can see I have gone from the vector notation to no vectors because I have already defined a direction that is oscillation is happening in this one dimension. And my force is always opposite to your displacement. Okay, so I have already considered the direction of this quantity, okay? And mass times acceleration, well, what about your acceleration? We know acceleration is dv dt, and velocity is dx dt, right? So acceleration is the second order derivative of your position with respect to time. So I will write acceleration using position as well. So you can see now your expression is using variable x, and this is a differential equation for your position x, and you can solve it, okay? Even if we don't know how to do it right away, we could look it up and we can always find an answer how to solve it. So group a few things together, we get k negative k over m x. A lot of times people call sorry, people call K over M to be angular frequency. So this K over M is defined to be omega squared. So you can write this using negative omega squared times X. Okay. All right, so we're not in, well, okay, so in physics, when we solve differential equations, we're not too concerned about the step-by-step approach. Mostly is, well, can you find a solution? You can even guess a solution. If you guess a solution and it works, then you're done. But it's good. Now, if you're taking a math course, they will tell you, okay, what is a step of solving a differential equation? But in physics, we just want to be able to find a solution. Once you're familiar with this type of equations, when you see something like this, you right away you will see something called, oh, this tells me this is a wave equation. This gives me a wave solution. Okay. How do we know? Because the wave solution is another model that's used in physics a lot. Basically, it tells you a spatial change of something, relating the spatial change of something to the time change of something. So you have both position and time in your differential equation. So we see this right away, we know, oh, this looks like a wave equation, and I know what the solution for that is. It's a sine pseudo function. Even if you're not so sure, you could always guess a solution and simply verify this. So a general solution to such a differential equation can be written using a sine pseudo function. Here I'm using a cosine with some amplitude and some angular frequency omega and some phase. We will talk about what each terms means. Okay, so right now you see a bunch of symbols, but we will make sense out of this later. So I claim this is a solution that satisfied the differential equation you had just derived. How can I prove that? We can prove this by plugging it in. So let's plug it in to see if it works. So we're going to plug this in. We get, okay, we want to take the second order with respect to time. So let's take it the first order first, and then we do the second order. So taking this with respect, derivative with respect to t, what do you get? Get a cosine become a negative sine. So a times omega, right? Because omega is in front of t, sine omega t plus phi. And you do the second order. So you take derivative with respect to this one more time. Okay, so sine becomes cosine, and you have another omega, so omega squared, cosine omega t plus phi. Right? So this is the left-hand side of my equation. See, this is the left-hand side. What is the right-hand side? The right-hand side is negative omega squared times x. So this is my x. So negative omega squared times x is indeed equal to my left-hand side. So I have proven this is indeed a solution to my differential equation, and this is the solution I need for the position of my mass. Okay, so this is the process to solve for your equation of motion. You might realize, okay, you still have a lot of these constants. So you had already told us what omega is. Okay, so we know what omega is, but what is A and what is phi? Okay, so again, the general procedure in physics was to find a general solution with a bunch of constants first, and then you can use your initial conditions to figure out what are the constants. So what are initial conditions? Is okay, where do you let go of the mass? That's considered an initial condition. So there are many different initial conditions, but for example, we're saying, okay, I start my timer, let's say, okay, when do you call t equals 0? Because that's all arbitrary. You can call this time t equals 0, or you can call this time to be t is 5 seconds, right? When do you want to start the time? So we'll say initially, let's start our time when your object is at a position when it's fully stretched, when your spring is fully stretched, and then t equals 0, you let go. Okay, so that starts our process. And then you can say, okay, under that initial conditions, I can tell you exactly where the position of the object is at a given time. So you can see that at time t equals 0, the object is not moving yet because you had just let go. So the velocity is 0. And the position of the object is at the fully stretched position is at distance d. So those are my initial conditions. I can plug in these initial conditions into the equations I had just found. So I found this equation. I will use my initial conditions to tell me what these constants has to be. Initial conditions is at t equals 0, the position is at a fully stretched distance, and the velocity of the object is also at 0. So let's plug in t equals 0. So according to my equation, at t equals 0, this is a cosine 0 plus phi, and that has to equal to the d, which was given. So by observing these two sides of the equation, I conclude, well, I need phi to go to 0. I need a to be equal to d, because cosine 0 is 1. So I get these two equal to each other, right? So I have solved all my unknowns. I can finally conclude the equation of the motion for the mass is d times cosine omega t, and there is no phase phi. Okay, phi is 0 in this case. So that's it. That's really what is telling you about the motion of this object. Okay, so what does this mean? This is telling you, okay, this is my spring. This is my spring. This is 0. This is d. This is telling me, okay, at t equals 0, this is fully stretched. At t equals 5 seconds, I can plug in 5 seconds, and then I can tell you exactly where this location is. It might be positive or it might have gone to a negative position. So it's telling me exactly where the object is at a given time. So this is the equation of the motion of the mass. Okay, so that's how we solved it. You can see this is the answer we just derived. Omega is square root of k over m. So this is what we call omega is an intrinsic nature of your oscillator, because once you fix a spring, you select a spring, whichever spring you want, you select mass, whatever mass you want to attach to it, then you have decide your omega. It does not depend on when you let go, how much you stretch it. It will always have the same omega. It will always have the same angular frequency. Okay. All right. So from that equation of motion, we can get two more things. One thing is the velocity of an object. That is simply derivative of position with respect to time. You can see a cosine derivative becomes sine, negative sine, and you have a omega when you do the derivative, right? Negative omega d sine omega t. Well, I'll tell you the velocity of this object is oscillating according to this formula, which means when your t equals 0, it has 0 velocity. When t is when whatever t is that allow your position to be 0, your velocity is maximum, because cosine and sine there, you can see they're out of phase, right? One maximum, one is 0. One is 0, one is maximum. Well, that makes sense. That we know that is exactly how our velocity of this object behaves when it's attached to a spring. And we can also get acceleration and just take the derivative of velocity with respect to time, and you get this equation. Okay, so that's all of that we derived from just using Newton's second law. If you want to plot the velocity of your graph of your velocity and acceleration, there are also sine zero. One of them is a sine function, one of them is a cosine function. And the constants in front of it tells you the maximum value these objects, these quantity could have. All right, sorry, we're out of time. So on Monday next week, we'll continue to talk about simple harmonic motion. And we will revisit this graph at the beginning of our class. Okay, bye everyone. Have a
Professor.
good, yeah.
Oh, could you send an email for like or on Canvas for like the last question on the homework? I can't solve that, so
Okay, so yes, I will.
okay, thank you.
Okay, sure, no problem. All right, I'll see you guys next week. Have a good weekend, everyone.
Bye, Professor. Have a good weekend. See you later.
Thank you. Bye-bye.
Thank you, Professor.
Professor, have a good weekend.
Thank you, you too.